The study of our Sun, our closest star, called heliophysics in technical terms, is one of the most fascinating topics of study in all of solar science. The Sun has an undeniable and quantifiable impact on our daily lives here on Earth, but its effects are also far-ranging, right out to the very edge of the solar system. One key area of interest over the past decade or so has been the study of the Sun's atmosphere, those being the outermost layers of superheated solar material called the photosphere, chromosphere, and corona. In particular, it's those last two layers that are of peak interest right now, to try and understand how events emanating from these layers, such as coronal mass ejections, solar flares, and magnetic storms, directly interact with Earth's atmosphere and solar system weather in general. It may seem quite a difficult thing to study from here on Earth, and it can be, because to truly understand the nature of the Sun, you have to get very close, or at least as close as you can. A few spacecraft have ventured the Sun's way, with the Parker Solar Probe actually going so far as to fly through the corona a few years ago. The SOHO spacecraft, a Sun observation satellite jointly operated by the European Space Agency and NASA, has been studying the Sun since 1996 from a point in space called Lagrange Point 1. It's gathered a massive data during its 28 years in deep space, but with advances in technology, it's time for a new spacecraft to come along. Enter India's Aditya-L1. It was launched on board a PSLV XL rocket on September 2nd, 2023 from Satish Dhawan Space Center on the west coast of India, and successfully deployed. From there, it performed a series of orbit-raising maneuvers before breaking free of Earth's orbit and then undertaking 4 months of travel to arrive at its destination, some 1.5 million kilometers from Earth, and that was on January 6th, 2024. Which sounds pretty far, but it's actually only about 10% of the total distance to the Sun. Lagrange Point 1 is one of several points which are not so much fixed points in space, but fixed distances between the Earth and other spatial features. In the case of L1, it's the distance between the Earth and the Sun, at which both bodies' gravitational forces cancel each other out, allowing a spacecraft to remain equidistant between both. In other words, because the gravitational forces cancel each other out, there's no pull greater than the other to draw the spacecraft back towards it. And because it's not a fixed point in space, Aditya-L1 is actually in a halo orbit. But Lagrange Point 1 offers full uninterrupted views of the Sun, which is crucial for effective study of solar occurrences. And because it's in a point between the Sun and the Earth, it can monitor and measure solar events as they break free of the corona and head towards Earth. It's like having a wave monitor in the middle of an ocean between two continents, except it's in space. Now, while we know a lot about our closest star, the interaction of solar magnetic storms with other planetary bodies in the solar system is still somewhat less understood. And neither is how the Sun's radiation affects Earth's atmosphere from short to long term. What causes all this to happen? And how would it impact a long-term habitation on the Moon or Mars? These are questions that Aditya-L1 will seek to answer in more detail as we move towards sending humans further out into the solar system than ever before and for longer than before. It will also look to answer one of the biggest questions about the Sun. What exactly happens in the layers below the corona that leads to a solar eruption happening? And how do these events cause solar winds to accelerate? While early models of solar winds understood that the product of a solar eruption was the ejection of charged particles, they failed to understand the acceleration mechanism. In other words, why are solar winds ejected from the corona at super high speeds? The models relied on the theory that thermal energy was solely responsible, but it's now believed that a combination of thermal energy and magnetic field disturbances is most probable. In 1995, the Ulysses probe observed solar magnetic switchbacks for the first time, whereby there's a sudden reversal and then correction of the polarity of the magnetic field of solar winds. A model was then developed which leaned on the theory that these were caused by the interaction between open and closed magnetic loops. with the Parker Solar Probe's observations in 2018 appearing close to this model. The Aspects, Papa and magnetometer instruments on board Aditya-L1 will look to study solar wind, looking for switchbacks, and to understand their effect on space weather in general. On January the 11th, 2024, the magnetometers successfully deployed at distances of 3 meters and 6 meters from the spacecraft. Now, this is handy for preventing any electromagnetic interference from the systems on board. The magnetometers at this position will allow data to be collected about the interspace magnetic fields between the Sun and Earth, as well as the general intraspace magnetic environment. Aditya-L1 will also be studying the corona much more closely than ever before, with the bulk of the instruments being for coronal study. These remote sensing payloads include a visible emission line coronagraph, which is a telescope capable of filtering out direct light from the Sun to focus on the outermost layer, a solar ultraviolet imaging telescope for imaging the photosphere and chromosphere in both narrowband and broadband frequencies, a low-energy X-ray spectrometer, and a high-energy X-ray spectrometer. These instruments will all help to study chromospheric and coronal heating, partially ionized plasma, the origins of coronal mass ejections, heat transfer, and flare exchanges. It will even use AI to help detect CMEs earlier than ever before, allowing for longer duration study and advanced weather warnings for here on Earth. As Aditya-L1 moved towards the Sun through December 2023, it sent back its first batches of X-ray images in a wide color spectrum from onboard sensors, and you can expect many more of these during the course of its planned 5-year mission. In fact, it'll be sending back an estimated 1,400 images per day from its VELC imager alone. However, like all good Star Trek shows, and Soho before it, I wouldn't be too surprised if it stays operational long after this. Hopefully, though, it doesn't replicate Soho and go off course, getting lost for 20 odd years in the process. It's not bad for a mission costing around $50 million US. We'll be keeping up to date with Aditya-L1 over the course of its lifetime, so make sure you're subscribed to the channel and follow along with me on X. Drop a like below and let me know your thoughts in the comments. I've also just released a batch of space-themed merchandise. Maybe you'd like to see some ISRO mission-inspired items in there. Let me know and check out tomjune.com for all the links. A massive thanks as ever to my amazing Patreon supporters who help to keep this channel going and make these videos happen. Thanks for watching, and I'll see you next time.